Now that we have some understanding of reflection and interference, we have the ability to observe a phenomenon called standing waves and then explain what's going on to create them. There's two big ideas here. One is what's a standing wave and how is it created? And the other one is what are the mathematical relationships that we can use to describe them or to predict them or to relate different characteristics. So pretty simple idea that gets into some pretty cool series math. I found this video on YouTube that would be sort of most similar to what I would do in class, where we'd be holding a spring across the room, and one of you would be right here holding it, and then we just kind of try to create some waves. And that's what he's doing right now. He's sort of explaining how he's going to send a pulse, and you can actually see him send it, and it will reflect. There it is. Right? And it came back, fixed end, inverted. By the way, you can also see if you watch this, you'll see it transmit into the new medium that is this guy's hand, which is a pretty cool, way to think about it. And then what's going to happen here is he's going to try to start oscillating his hand in a way that kind of times it perfectly, that he sends a new pulse just as the old one is getting back there. Do you see it transmit into his hand? And there's maybe a little too much talking. Here it is. And he makes this thing that's effectively called a standing wave. The reason it's called a standing wave is it doesn't seem like it's moving, traveling. In reality, there is traveling, and we'll explain what's going on. But in reality, this is an interference pattern between the incident wave, a continuous incident wave, and its reflection. So, very cool. Now, what he's going to do next is increase the frequency of his source oscillation. And look at this. He creates, it's kind of really cool whenever I pause it because it can be paused in lots of different areas. But what we have here is almost like two different loops. And you'll see this, there's this point right here that never seems to move. And there's a term for that, it's nodes. This is a node too. Even though he's going up and down, it's not this type of amplitude. The amplitude here, this position of maximum amplitude, is called an antinode. And then this is a node, here's another node, and then in here is an antinode. But this point never moves. And even though the oscillation is coming from his hand, it really isn't moving much anyway. And these are huge amplitude compared to the little oscillation that he's actually producing. So he was able to create it. Now, a key piece of that is that any frequency in between his first two frequencies would not produce a standing wave because it wouldn't be the right frequency to produce a standing wave. So then he kind of goes on here. Eventually, he tries to get the third member of the standing wave series, and he kind of fails, and I wish he would have done better. Come on, you can do it. There it is. Do you see it? All right. There's an antinode. Sorry, antinode, antinode, antinode. These are then more nodes. This point really doesn't move. It doesn't stay there for long. There it is. Then he goes to notice nothing happens here at the wrong frequency. There's only certain frequencies that will produce standing waves. It's a really big idea. And then he finally tries to go to there it is. It's like a 1, 2, 3, 4 loop standing wave. So he did a nice job with that one. And this is sort of a picture that I got again from Dan Russell's website. It's kind of a moving GIF that shows what's really going on, and this is how we would see it. We could pause it at any point here, kind of like in the videos. This is what it really looks like. And then these above here is these pictures that are frequently depicting standing wave. And it's key to kind of know that this top one here is not what's really going on. It's just kind of the time average of what's going on. At any given point, it could be any of these, right? But we draw these in such a way to show these loops. So like 1 loop, 2 loops, 3 loops. And it's key to know that what we're doing is we're taking the same amount of string length and dividing up into more and more loops. On this first one, you could see the position of nodes, antinodes, node, and you could then go ahead and do that with every one of the standing wave series. And kind of look at like, here's these lines where nothing's moving. Anything along a green line is a no motion part. Anything along a red line is a maximum motion. That's the maximum amplitude right there. We're going to develop the mathematical equations to describe this series because there's a lot of math here. And you can kind of see, I mean, the easiest math is really around this idea that we're taking a given length L and we're dividing it up into a whole number of sections. So this is 1 section, 2 sections, 3 sections, etc. All right. Now, a key to recognize this is like a 1 wavelength would be this long. Do you see it? That's 1 wavelength right there. So this, member of the standing wave series has a full wavelength within length L. This one has only a half wavelength. Therefore, each one of these loopy sections is a half wavelength. So this has 2 half wavelengths, right? And so if we were to try to write L in terms of half wavelengths, this first one here, we would say that L is equal to 1 half wavelength. And here, L is equal to 2 half wavelengths. Here, the length L is made up of 3 half wavelengths. And on and on. And so we've actually written an equation that is very common except for this term right here. And that's a mathematical series. If we solve for wavelength, this column is just this column solved. We would multiply through here by 2, and that's going to be on the numerator for all of these, divided by this number here. And if we did that, we'd find that there's an expression for wavelength that is in terms of this almost reference number. So that's a good time to introduce the idea of the index number. N is just what member of the series it is. Some people will always try to connect this to nodes and antinodes. Be very careful with that. I just think it's too confusing to do that. You could say, I want to tie this to something physically about the standing wave. And you can kind of see here that physically, there's 1 antinode, there's 2 antinodes. If you want to memorize that for a standing wave series fixed at both ends, that N is equal to the number of antinodes, you may do that. I just think eventually you're memorizing so many rules instead of just looking at the pictures. So, but N is just the index number for the mathematical series. That allows us to kind of give a general equation for a standing wave series. Now, this equation is not on your equation sheet, and that's what's maybe a little bit confusing at first about standing waves. You sort of have to be able to use what is on your equation sheet, which is the wave speed equation, to kind of understand these. The idea here, though, is that we always have a whole number of half wavelengths in here. 3.5 half wavelengths does not work. 3 or 4 does. Now, how do you produce wavelengths? We know that wavelengths are a product of speed and the oscillating frequency of the source. So the only 2 things that you can do to control sort of the wavelength is to change the speed on this and to change the frequency. Well, in a given medium at a given tension and a given string, there is no change in velocity. So the only thing you can do really if we wanted to say have the wavelength in going from this member to this member, we would have to double the frequency. Now the specific frequency that is, we just would call F1. It'd just be like the frequency required to produce this. And then in order to get to this, we would go to the second frequency, which would be twice F1. And this one has a wavelength that is 1/3 of this one, so this one will be 3 times that, right? And we would see that pattern. This one, 4, 5, 6 times that. And so in order to get the frequency of subsequent members of the standing wave series, you just multiply it by whatever the index number is. And then we could say that the frequency of the nth member of the standing wave series is simply the first frequency times n. Now these are related by the idea that v is a constant. And so using the wave speed equation, v equals lambda f, we could find this speed here by lambda 1 f1. And this speed would be lambda 2 f2. Now, what you would not get for a correct speed is if you multiply the wavelength of the second member of the standing wave with the frequency of the third member of the standing wave. It's these two have to match. But every product of wavelength and frequency for a given member of the standing wave is the same constant speed. What happens when we change speed? That's something we're going to get to when we talk a lot about sound, because in so many sound and instrument applications, standing waves are the key to understanding what's going on with creating that sound. But for any member of the standing wave series, these n and n have to match. It can't be n. It can't be 4 and 2. But if that's the case, then the product is a constant velocity. There's some terms for this. This is often called the fundamental frequency, or the fundamental. This is often also called the first harmonic. And this becomes like, the second harmonic or the third harmonic. And in general, you can always call any of these like the nth harmonic. Well, what's going on here? And for that, we're going to go back to Walter Fent's standing wave reflection. The other day we had these turned off, and all I wanted was the wave just to kind of show you what was going on. And I have some settings here that we now know a little bit more about from a fixed end. This is the fixed end. Okay. Now, before I never put the actual waves shown. So the functionality on this is way cooler if you put the actual incident and reflected wave and then let it go. So you can kind of see the incident waves, and they're going to continue, but as soon as it gets reflected, you're going to see the reflected standing waves. It's fixed, so it should be reflecting on the other side or inverted or out of phase, and then here it comes. Now the actual dotted line here, which is the standing wave, is the sum of the incident and reflected waves. The reflected wave is interfering with the incident wave, or the incident wave is interfering with its reflection. And if we have created a wavelength in which there are a whole number of half wavelengths, right? Wait a little more. When they say slow motion, they mean it. So this is the point approaching when the incident wave is going to be completely constructively interfering with its reflection, right? There. The incident and reflected wave are right on top of each other and constructively interfere. And look, 1, 2, 3, 4, 5, 6 half wavelengths in this one. Keep going a little longer. And this is when they approach complete destructive interference. And at this point, this is when the wave itself kind of moves through the middle. So just kind of keep watching that, and I'll put the link in the page below. So if you want to just watch that for a while, it can kind of rock you to sleep a little bit. That'll be nice. So now it's sort of time to let you loose on some problem solving, and you'll be doing, you can look at any of these resources, but you eventually have to get to the point where you're using some of the mathematical equations. So I've got some tips for standing wave problems as we just venture into this. Number one, make sure you draw a correct standing wave. Draw a diagram of a correct standing wave that corresponds to the one that's described in the problem. If there's a picture, that's great, but otherwise you're going to have to translate the description into a picture. Make sure you know what the boundary conditions are. Now, we haven't learned any other boundary conditions. They're all fixed at both ends for tonight. But tomorrow, I guess that's not tomorrow. I guess that's a week and some change from now, be introducing the different boundary conditions. Although this is the most time we're going to spend on developing this. So how many nodes and antinodes? Did they talk about that? I mean, don't memorize rules. Draw them. Count them. Do the number of nodes in your drawing, does it match what was stated in the problem? And then find the wavelength. How do you find the wavelength? Well, you're usually going to use an equation. After you use an equation, though, like if you're doing the 2L over N, look at your drawing. Does the answer you came up with make sense? Can you identify how many half wavelengths or even how many whole wavelengths are in there, and does it make sense? Don't just be an equation robot. Do you fundamentally understand what's going on? And then really when you're trying to relate wavelength is really just a function of the picture often and seeing it. But how do we produce that? How do you see wavelength as a product of V and F? Now, if all of our speeds are constant here, how does F change to create wavelength? Wavelength and frequency are inverse is what that equation is showing. And if the product is constant and is the wave speed, then as this goes up, this one goes down. So good luck. Any problems you're having with the homework, make sure you put it in the discussion thread. So thanks a lot.